Cauchy Goursat Theorem. Let fz be analytic in a domain containing rectangle C and its interior, then integral over that C fz dz is equal to 0. Here this closed contour is your rectangle and it has been divided into 4 equal congruent rectangles. Now Goursat uses the Cauchy's weak theorem here to prove this theorem, and also there is no assumption, that is the continuity of f dash set, because Cauchy's weak theorem requires that, which says if fz is analytic with a continuous derivative in a simply connected domain D and C is the closed contour, then this integral over C fz dz is 0. But Goursat, without assuming the continuity of f dash z, he uses the Cauchy's weak theorem and prove this theorem, that is integral over C fz dz is equal to 0. So let's start with the proof. Now here it is taken closed contour as your rectangle and it has been divided into 4 equal congruent rectangles. Now what will be the path followed in them? Suppose this is rectangle C1, this is C2, this is C3, this is C4. What path C1 follows is that where the domain, that is domain should be on the left hand side of the path followed. So arrow starts from here like this. Here the domain is on the left hand side and then this C1 rectangle path is completed. For C2 again domain should be on the left hand side, so I'm starting this path as the orientation like this. Now here the orientation is opposite to that of C1, so these two cancel each other. Likewise C3, which starts like this, the domain is on the left hand side, so it completed this path. Here also these two directions are on the opposite side, so these two cancel each other. Then again in C4 we again start from here, the domain is on the left hand side and this path is completed like this. So the opposite orientations, all these are cancelled each other. So now let's start with the proof. Okay, so integral over C, first I should write divide rectangle C into 4 congruent rectangles. Congruent means all the sides, all the angles, all the rectangles are same. So if this is C1, C2, C3, C4, then all rectangles can be taken as C1, 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 C1 because they are congruent to each other. So it follows that integral over C fz dz is equal to integral over C1 fz dz plus integral over C2 fz dz plus integral over C3 fz dz plus integral over C4 fz dz. So by triangle inequality, if I take the mod let's take the mod of integral over C fz dz. If I take the mod, then this mod is less than equal to sum of the mods of all the integrals C1 fz dz plus mod of integral over C2 fz dz plus integral over C3 fz dz plus integral over C4 fz dz. Okay, all right. Now all the rectangles are congruent, so can I write C1, 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 C1 and take this as 4 times mod of integral C1 fz dz? Yes, because rectangles are congruent. So the expression becomes integral over C1 fz dz. This 4 can be taken on the other side. This is greater than equal to now mod, this is 1 by 4 integral over C fz dz mod. Take this as 1. Next, now since I have divided the C into 4 rectangles, now if you consider this only C1 rectangle, now again I divide the C1 rectangle into 4 equal congruent rectangles and name one of the rectangle as C2. Then again C2 is subdivided into 4 rectangles, then C3, C4 up to so on, up to this last rectangle is your Cn. Alright. So as above, for at least one rectangle denoted by C2 we have, जैसे हमने C1 के लिए ये बनाया, similarly for C2 also we have the same inequality, that is this mod is greater than equal to 1 by 4 integral over, now here this integral is over C1 because in the previous one C is divided into 4 rectangles, so we taken any one of them as C1. Now again C1 is divided into further 4 rectangles and we take one of them as C2 and write this expression. Alright, so this is equal to 1 by 4 mod of, what is integral over C1? This is 1 by 4 C fz integral over C fz dz. So here it becomes square now and it is replaced by C fz dz. Is it clear? Okay, alright. Take this as 2. Yes, this integral over C1 because it is greater than equal to C, so I should write here also greater than equal to. Next, now continuing like this process, we obtain a nested sequence of rectangles Cn, each satisfying this inequality. So as a whole, I write continuing like this. Sorry. We obtain the nested sequence. Cn, and now I write mod of integral over Cn f of z dz is greater than equal to C. Here the number is 2 and the power of 4 is also 2. So if this is n, so the power of 4 is n, mod of integral over C f of z dz. Is it clear? Take this as your 3. Now if you continue like this, you have so many rectangles, like this is your nested sequence of these rectangles. Now there is exactly a one point z0 say belonging to all the rectangles. एक ऐसा point आपको यहाँ पर इस Cn के अंदर मिल सकता है जो सभी के सभी rectangles को belong करेगा. Obviously जो Cn के अंदर है वो बाकी सभी rectangles के अंदर तो belong कर ही जाएगा. So let's say that point to be at z0, which is present in this Cn. Now for each n, the point z0 is, now z0 can be inside Cn or either on the Cn. There are two possibilities. the z naught is either on or inside the rectangle Cn. See, it can be inside Cn or it can be on the rectangle on the rectangle Cn. So in particular, if you look, this z naught is in the domain of analytic of fz. Obviously, this is a closed contour C, and this closed contour is this whole C, that is your closed contour, that is your rectangle. It is contained in this domain D. So z naught is also in this domain D, where your function is analytic. So in particular, z naught is in domain of analyticity of fz. So in particular, z naught is in the domain of, because fz is analytic in the domain, it is given of f of z, analyticity of f of z. So for given epsilon positive, there exists delta positive such that the derivative for fz is existed because it is analytic, so it is differentiable everywhere. So I write the definition, that is f dash z naught. The derivative of f at z naught is equal to limit z tends to z naught for all z, alright. So this is f of z minus f of z naught over z minus z naught. So this implies, that means if you do not write this limit, then this can be written as f of z minus f of z naught over z minus z naught minus f dash z naught mod is less than epsilon for z minus z naught less than delta. So this implies f of z f dash z naught is equal to, can I write fz minus f of z naught over z minus z naught minus eta z. Is it clear? No. Okay. If I write like this, since this mod is less than epsilon, let's take f of z minus f of z naught over z minus z naught minus f dash z naught. This is equal to eta of z, let's say eta of z, where this eta of z is less than epsilon. Now is it clear? Yes. When z minus z naught mod is less than delta. So this is equal to, okay, here mod is not present, sorry. Whenever this mod is less than epsilon, we can take like this, where eta of z is less than epsilon. I have mentioned a new term over here for epsilon. So this now becomes f dash z naught is equal to, I take this on the other side and take this here, LHS on the right and left hand side. So this will become f of z minus f of z naught over z minus z naught minus eta of z. Is it clear now? Alright. So if you solve this, you take LCM. So you will get f dash z naught, z minus z naught, plus this eta z comes over here, z minus z naught is equal to f of z minus f of z naught. This implies f of z is equal to f of z naught plus f dash z naught into z minus z naught plus eta z z minus z naught. So now taking the integral over Cn, because we have talked about Cn, dz is equal to integral over Cn f of z naught plus f dash z naught z minus z naught plus eta of z z minus z naught dz. I am taking the integral over here also. Just take these together and take this integral over this term. So now if you look the first integral, if you take the derivative of this whole term, of these whole terms, then you will see that this derivative is continuous because the derivative for all these terms is constant. So you are having the continuous derivative for this function, whole function. So whenever, now Cauchy's theorem says that whenever the function having the continuous derivative in the closed contour, then the integral over that function is 0 along that closed contour. So here if we look at the derivative for all these terms, this will be a constant. So the function having a continuous derivative. Let's check. Derivative for this is f dash z naught plus first function derivative of second, that is 1, plus second function derivative of this, since f dash z naught, this is a constant, so derivative is 0. Alright, because z naught is a point. So now this is also constant, this is also constant, and this is 0. So you are left with this only, which is a constant. This is also constant and this is also constant, and this is 0. So you're having the constant derivative. The derivative of this whole function is constant. This implies the derivative is continuous for this whole function. So by using the Cauchy's theorem, this whole integral is 0, because Cauchy's theorem says that integral over closed contour, that is if your contour is here Cn and the function having the continuous derivative, then whole integral is 0. Here Goursat uses the Cauchy's theorem, Cauchy's weak theorem. So by using the Cauchy's weak theorem, integral over Cn f of z naught plus f dash z naught z minus z naught, this whole integral is 0. So we have left with integral over Cn f of z dz is equal to integral over Cn eta of z z minus z naught dz. This is okay. Now choose n large enough so that Cn is contained in the neighborhood of z naught delta. Suppose this is your point z naught in Cn. Now you took your n to be so large, C1 के अंदर C2 फिर C3 C4 C5 C6 up to so on, and इतना ज़्यादा लंबा large ले लो, so that अगर हम z नॉट की नेबरहुड बनाते हैं तो आपका जो रेक्टेंगल है वो इसकी नेबरहुड के अंदर आ जाए, so that this rectangle Cn is contained in the neighborhood of z naught. So choose n large enough so that this Cn rectangle is contained in the neighborhood of z0 delta. So then taking the mod integral over Cn fz dz, this mod is equal to taking mod on both the sides, eta of z minus z0 dz. Now eta z is less than epsilon. Eta z is less than epsilon. Using this, this mod is less than equal to first Cn eta of z mod of z minus z0 and mod of dz. Now this is less than equal to, this is epsilon, alright. Integral over Cn z minus z0 mod of dz. Now what is dz mod? And what is mod of z minus z0? See, this is your rectangle Cn. This is your point z0. If you take another point from this rectangle, let that be z. The distance between z and z0 is less than equal to the diagonal of this Cn rectangle, that is dn. dn is the diagonal for this Cn rectangle. So the distance between these 2 points is less than equal to the whole diagonal. Okay, so this implies, let I write this as less than equal to dn. So before we should write let dn be the diagonal of rectangle Cn and let ln be the parameter of this rectangle. ln be the parameter for this rectangle. Then if this happens, then this distance between z minus z, that is z and z0, is less than equal to dn for all z in Cn. सभी के सभी z जितने भी Cn में प्रेजेंट है, उन दोनों का डिस्टेंस जो है वो डायगोनल से लेस ही है. So therefore mod of Cn fz dz, this is less than equal to epsilon, and instead of mod of z minus z0, I am writing dn and integral is left with this dz. So this is epsilon, this is dn. Integral over mod dz is nothing but it is your parameter of the rectangle Cn. So I am writing ln. Alright. This is equal to epsilon into. Now what is dn? dn is half the power n of d. How? See, suppose you are having this rectangle C2 and this is the diagonal of the rectangle C2. C2 is divided into 4 parts in equal congruent rectangles, and let name this rectangle as C3, and this is your diagonal of C3, that is D3. Now if you look, this D3 is half of D2. So D3 is half of D2. So in further on, D3 is half of, what is D2? Then D2 is also half of D1. See, D3 is half of D2. D2 is again half of D1. And D1 is again half of D. So इसकी पावर 2 की बन जाएगी 3d. So d3 is 1 by 2 cube of d. Now here the number is 3, here the power is 3. So can I write for dn that dn is equal to 1 by 2 the power n of d? Okay. So this dn can be written as half the power n. Here this is n, so the power should be also n, half of this d. Similarly, parameter is also half of the previous rectangle. So in total ln is to the power n of d. जैसे हमने डायगनल को देखा है, सिमिलरली अगर हम पैरामीटर की भी बात करेंगे, C3 का पैरामीटर इज हाफ ऑफ दिस C2. सो अगेन C2 इज हाफ ऑफ C1. चलते चलते फिर से हमारे पास पावर 1 बाई 2 द पावर n ऑफ L बन जाएगी. जो L जो है मेन पैरामीटर, जो आपका जो C रेक्टेंगल जो हमने स्टार्टिंग में कंसिडर किया हुआ है. सो कैन आई रब दिस? Just think over this, you will get the result. Next, this is equal to, sorry, this is L, not diagonal, because parameter is denoted by L. So this is L, where D is the whole diagonal of the given rectangle C and L is the whole parameter of the given rectangle C. That rectangle which is subdivided into further so many congruent rectangles. So this is epsilon, this is dl over, this is 4 the power n. So where D and L denote the diagonal and parameter of C respectively. Alright, so this implies epsilon dl over 4 power n. This is greater than equal to this integral. Because अभी हमने cn fz dz वाला जो इंटीग्रल है इसको भी हमने देखना है. दिस इज फ्रॉम 3 जो हमने पीछे मार्क किया था. देखो this integral is greater than equal to 1 by 4 the power n integral c f z dz. ठीक है, यहाँ से from 3 हम लिख रहे हैं this integral is greater than equal to 1 over 4 the power n integral over c f z dz. So this implies integral over c f of z dz mod is less than equal to 4 the power n, 4 the power n cancelled out. So we have left with epsilon dl. Now epsilon is arbitrary as epsilon was arbitrary. So this whole integral is equal to 0. Therefore, integral over c f z dz is equal to 0. If mod is 0, then integral over c f z dz is 0. Hence the proof. So interesting proof, है ना? Next, there is a short theorem. Let's understand that. Let fz be continuous in a domain D. Let fz be continuous in a domain D. And suppose there is a differentiable function fz. Let And suppose there is a differentiable function fz such that इसका अगर हम डेरिवेटिव लेते हैं दिस इज इक्वल टू एफ ऑफ जेड इन डी अगर हम डेरिवेटिव लेंगे दैट इज ये जो डिफरेंशियल फंक्शन है सच दैट एफ डैश जेड इज इक्वल टू एफ जेड इन डी then for any contour C in D which is parameterized by ZT we have the integral is f of ZB minus f of ZA. Then for any contour C in D parameterized by ZT where T is from A to B we have integral over C f of Z dz is equal to capital F of ZB minus f of ZA. How we prove this theorem? Since fz has a continuous derivative in D, it is given. Since fz has a continuous derivative in D, so integral over C f of z dz is equal to, it is given that this fz is equal to f dash z dz. Further, how should I write this? Okay, instead of contour I should write the limits a to b because it is parameterized. So this is f dash, instead of z I should write z of t, and instead of dz it is z dash t dt, which is equal to integral over a to b. Now f dash zt can be written as z dash t d by dt, that is a derivative, this is nothing but the derivative of f of zt. Okay, the derivative with respect to t of this will be f dash zt साथ में z dash t dt. ठीक है, इसको ऐसे भी लिख सकते हैं. So this is equal to, now since it is an integral and this is a this is your differentiable function, so this will be equal to f of z upper limit minus f of z the lower limit, hence the proof. So next time we will examine the relationship between antiderivatives and analytic functions. We do some more theorems and plus examples based on these theorems. So let's meet in the next class. Thank you for watching this video. Thanks. Watching.